Okay, can you guys hear me? Just want to make sure that the sound is okay. Well, first of all, welcome everybody. This is episode 88 of Axioms on Trial. Today we're going to be talking with Dr. Ruth Kastner on issues of philosophy of science and quantum theory. Okay, great. I'm glad you can all hear me. So I'm gonna bring her right on. So there we go. Thank you so much for coming.
You're very welcome. Thank you for inviting me.
So if you could give a little bit of the audience your background, what do you do, and what is your field of expertise?
Well, my background is I actually started out in physics. I was pursuing a higher study in physics, and I got to the master's level, and I started getting very interested in non-locality and these kind of puzzles with the Einstein-Podolsky-Rosen experiment, which is the famous experiment where you have correlated particles like electrons, and you send them off to opposite ends of the galaxy, and you're making measurements on them individually, and they seem to be correlated in this very non-local way. So that really caught my interest, and I realized that the people that were really looking into that and investigating those issues were in the philosophy department. At the time, I was at the University of Maryland. So I switched to my major for my PhD study program of study to philosophy of science. And after that point, I ended up at that time, the group was called the Committee on the History and Philosophy of Science. So we were, the group studies the whole history of thought and in the physical sciences, and that was one of the areas they were studying. So that's kind of my background kind of came at it from the straight physics background, and then got kind of captured by the implications of quantum theory and wanted to study that in more detail.
What would you say are some of these implications, philosophically speaking?
Well, I mean, one implication does seem to be this non-local quality to quantum systems, this idea that they are, for these kinds of states where we have different, numerically more than one system that is described by this collection of systems is described by an overall state that has this holistic character that is very hard to understand in terms of just separate systems that we're used to identifying in physics. So they have these non-local correlations that seem to be in tension with relativity, which tells us that information, energy and signals and so forth cannot exceed the speed of light. And yet we have these mysterious correlations that seem to be influences that exceed the speed of light. So that's one of the puzzles. And of course, the challenge is figuring out, well, what are the implications? How should we understand reality in light of these kinds of puzzles? And I've argued, and we might get into that later, but I've argued that possibly one of the implications of quantum theory is that our world, our reality has an element of possibility that kind of goes beyond our usual empirical space-time realm. And that's what the quantum theory is describing. So that's one of the implications that I'm finding from quantum theory.
Could you elaborate on that one specific that I find interesting? You're saying an aspect of possibility. What do you mean
Right.
by that?
So, we think of our everyday experience. We have phenomena that are very concrete, we can really put our finger on everything and say, okay, I know how fast something is going and I can see where it is and so on. And that kind of information doesn't seem to obtain at the quantum level. We have Heisenberg's uncertainty principle. So the idea of possibility comes in when we're dealing with quantum systems such as atoms and electrons and so on, and photons that seem to have a potential for different outcomes. If we're doing a measurement, if we're going to observe them, say we have a system that's prepared in some state and we want to find out where it is. So we do a measurement to try to figure out where it is. It actually has probabilities for being in a bunch of different places. And yet, at the end, we do find a concrete location at the end of our measurement. But all of these possible outcomes I see as a feature of the world at a subtle level, so that I think of the quantum states as basically kind of giving us information about a level of possibility that is nevertheless real. And it clearly is consequential because we can prepare these quantum systems and we can interact with them and so on. It's not like they're figments of our imagination. And we always find one of the possible outcomes of a measurement with a probability that quantum theory predicts that it will have. So I like to I think the most natural way to interpret that is the idea that quantum theory is really pointing to this level of real possibility that's kind of in play beneath the phenomenal level of our world.
I understand.
Yeah.
One question that I've been meaning to ask, do you feel like there is somewhat of a miscommunication between physics or physicists and those that are doing philosophy of science? Like, is there a conflict there in the way that these things are talked about? Or is it more harmonious than maybe it appears to me?
Well, it's kind of gone through an evolution. I mean, back in the previous century, when Einstein and Bohr and so on, and the pioneers of quantum theory were coming up with this theory, they were very comfortable with addressing philosophical questions and philosophical issues. And they considered that part of an important part of theorizing in physics. So that tradition has been there. More recently, I mean, things kind of went through an evolution where towards the middle and latter part of the 20th century, when people started realizing how strange quantum theory was, there came about kind of a division where most physicists got into this approach of basically what I would call instrumentalism, which means using the theory as just an instrument or tool for prediction. So they just wanted to be very pragmatic about it. They were frustrated by the quantum puzzles and things like, there is something called the measurement problem, which is the fact that in the standard way of formulating the theory, there isn't really a good way of representing the measurement process and of explaining why you get outcomes and that kind of thing. So that's become known as the measurement problem, and that's represented by Schrodinger's cat. Erwin Schrödinger was upset about that too. So the response has largely been on the part of physicists to kind of say, okay, we're not going to worry about that. That's a dead end, and we're going to just apply the theory. On the other hand, there are some philosophers who have kind of gone that route and are being more instrumentalist about the theory. But there are still some philosophers who are trying to understand the meaning of quantum theory and come up with a better way of accounting for, measurement and so on, and understanding the implications of quantum theory for physical reality. So, it's kind of something that keeps evolving. there is some tension there. There is some tension there, and there's just a lot of controversy all around. I mean, even among philosophers who have very, very, very different ways of approaching the theory. So it's kind of all over the place in that way.
How do you feel about kind of the movement away from falsification as being a fundamental pillar of the way in which science is done? Do you
Yeah.
agree that is happening? Do you think that it makes sense, or do you think that it's problematic?
Well, yeah, I think that I kind of have mixed feelings about it. I think that Popper was certainly onto something when he noted that, logically, if you're kind of going out on a limb and saying, here's a prediction, here's what my model says, or here's what my theory says, go ahead, I'm willing to be shown that I'm wrong. And then you do observations and you come up with some results that really kind of cast doubt on the theory. That's good if you can do that. That is very good, because it's really, in a way, what differentiates science from other forms of thought where you just can go around in endless speculation and so on. Having said that, it's a very kind of well-known point that throughout the previous century, people were trying to use that, the kind of falsification criterion to demarcate science, good science from pseudoscience and good science from, other phony kinds of things. And it's really very hard to do that in real life. And in fact, what you find is, technically you could say, well, Newton's theory has been falsified, if just simply because it's a good first approximation to nature, but on the other hand, it doesn't quite get all the details right at the relativistic level, and so on. So we really have to be careful about, we obviously don't want to throw out a good theory simply because we're getting observations that are a little inconsistent with it. So it's a very subtle issue about, what counts as a falsifying instance or observation. But in terms of things like string theory, where you're getting whole theoretical constructions that even in principle there's no way to test them, you have to be a little careful. You have to use I have mixed feelings about that. Again, we can't just demand, it's not realistic to demand that any good theory be falsifiable. We know that that's true from looking at the history of science. So we can't just say, well, that's no good because you can't falsify it. But we do have to be very careful to not be engaging in kinds of ad hoc maneuvers, right, to keep a theory afloat when it's really not being fruitful.
Yeah, I guess that's my question too, is if falsification, it doesn't matter as much as I think it does, but then what tools do we apply to say, well, this theory is better than another one? How do we not fall into now accepting pseudoscience or, other, like you said, post hoc explanations that aren't actually getting at anything?
Yeah, that's a great question. And I do think we can do it by looking at anomalies. So when we have, an anomaly is a situation where we have some theories that, seem to work pretty well, but we've got these anomalies. And a case in point is the phenomena that have been usually attributed to things like dark matter and dark energy, which are observations of the large-scale universe, and the rotation rates of galaxies are deviating from our so far our best theory of gravity. So they're deviating from that, and that's an anomaly. So what we have is those galactic rotation, what they're called rotation curves, that are basically graphs that where the periphery of the galaxy seems to be going way faster than our theory says it should. So that's an anomaly, and it means that either that there's something wrong with the theory, or maybe there's some stuff out there that we can't account for, that where the theory would still be right, but we're just missing some mass, which is what dark matter is. Now, I consider the dark matter hypothesis as just one of those sort of post hoc kind of Band-Aid things where you want to keep wait, we like our gravity theory. So maybe it's right, and there's just some missing little element out there, that we don't know about. But in fact, and I've been pursuing, this sounds self-serving, but it's not just me, but others have been pursuing a different formulation of gravity, of general relativity, that's a more general formulation that, in fact, does accommodate, or predict just what's considered to be an anomaly in the current theory. So that's a really good, if you have kind of a prediction of a model that predicts what now seems to be an anomaly for your current theory, then that's kind of a good way of corroborating this candidate theory, where it's actually supporting the phenomena you're seeing that don't fit into your previous theory. So I think that's kind of a powerful testimony for a candidate theory.
I guess it's a good segue to ask you specifically what it is that your contribution has been in the field, and where does it differ from some of these other theories.
Well, my research has been on the transactional interpretation of quantum theory. And that has, it's called interpretation. Technically, really, it's a slightly different formulation of quantum theory. And it's based on a different understanding of the way fields work. So it's a bit of a kind of a radical departure conceptually from the way physics views field behavior. And it was originally proposed by John Kramer in the 1980s. That's how it got the name transactional interpretation. And it was based on the so-called absorber theory of radiation. So that theory that was developed by Wheeler and Feynman in the early mid-20th century. And it was also explored by others as well. Paul Davies explored that. And the absorber theory says that when charges like electrons, any kind of charged particle, a charged particle is basically a source of the electromagnetic field. So it has kind of an interaction with the electromagnetic field, which is our photon, our light, and light energy, and that kind of thing. So the absorber theory proposed that there's this time symmetry going on, and that any charge is actually not just kind of sending out a field that goes in the future direction or directed towards the future, but it also has a component that is past directed. These are called advanced fields. Now, as you might guess, that's a very strange notion. If we think that everything happens in our usual space-time container, which is another thing that I question, but that our usual idea is, well, anything that generates a field has to be causal, in the sense that it's got to generate something that goes from a certain time directed into the future. But according to this theory, charges actually generate a field that is time symmetric, and it's also kind of non-local. So it's not like the usual field that we have in standard quantum theory, which is considered to be sort of a freestanding mechanical system. But instead, this absorber theory has an emitter and an absorber kind of directly connected by a non-local kind of field, kind of an influence. So we not only do we have that, but we also, under certain conditions, have an active participation by the absorbers. So we have emitters and absorbers, and we can go into more detail about, well, what do you mean by emitter and absorber?
Yeah.
But, think of them as charges, right? And they can either give away energy or they can accept energy, right? So, but you can have a kind of a collaborative situation where the absorbers will respond in a way that is perfectly in sync with the field generated by the emitter. And that's actually how you get a what's called a transaction, which conveys real energy at the quantum level, a real photon, from the emitter to the absorber. So that procedure, what basically, as a shorthand, you could say you have an emitter-absorber transaction in which the emitter generates, and a bunch of absorbers usually will respond, and they respond, and the emitter gets this past-directed advanced kind of influence from the absorbers, which is called a confirmation in the usual way of talking. So we have like an offer and a confirmation, and we can have many confirmations. Those again are kind of the possibilities. So those, you have many different absorbers to which a single photon could go, and they can't all get this single photon. So that's where you get kind of a symmetry breaking, and you get the actualization of this real photon that goes then from the emitter to the absorber. And that at that point you have a kind of a local process. But at the quantum level, at the sort of more subtle level, everything that leads up to that is a kind of a direct connection that has this non-local character. So that's what I've been working on. Yes, it sounds radical and so on, but what you get from it is you get a good account of what is measurement. And the standard theory really cannot explain to you, you know, what are you doing when you're doing a measurement? What is the physical interaction that constitutes measurement? And the technical term for this is it's non-unitary. So that's just a fancy word that basically means it's there's a kind of a collapse or an actualization of one of these possibilities out of a whole set of them. And if you don't have that, if you don't have this real non-unitarity that you get, this direct kind of absorber response, this interaction that you only get in this transactional picture, if you don't get that, then you end up with Schrodinger's cat and those kinds of things, because you have no way of explaining, you know, what is it that's making, what is it that's precipitating a measurement result. So that's what you get with the transactional picture. And you also get an account of the probability rule from quantum theory called the Born rule. It's named after Max Born, which up till, you know, before the transactional picture, that was just kind of a recipe, a mathematical recipe that people would apply, and they didn't know where it came from. So you can very clearly see in the transactional picture in a mathematical way where that expression comes from.
So let me see if I'm following this,
Yeah,
because
sure. There's
physics
a lot,
is
a lot there.
my field is
Yeah.
philosophy, not science.
Sure.
So,
Mm-hmm.
so is the claim here that there is a relationship between the past and the future, where they are interacting with each other in some sense to actually give rise to the reality that then we experience?
You could say it that way. I think of it more in terms of there are relations, interactions among these quantum systems, which are, in a sense, kind of forms of physical potency. And when they're interacting, they're not really in the past or in the future. I actually think of them as kind of in an eternal present. They're sort of in a timeless, I call it a quantum substratum. So they're kind of in this timeless domain that is not part of the space-time construct. That are at a pre-space-time level. So I think of them as possibilities, but out of that interaction, we do get a temporal orientation. What we get is basically events. We get an emission event, and we get an absorption event. And if you like, if you think of it in terms of, say, there are absorbers in our eye, in our sense organs, in our eyes, and so on. So if we are absorbing a photon in our eye, then at that moment of that absorption, we are basically kind of helping to bring about the past, that we're participating in this transaction that in a sense is bringing about these events, and part of that is bringing about the past.
I guess the one point of confusion for me is maybe it's me struggling with my intuitions, and not knowing how to move away from that.
Mm-hmm.
But when I think of the notion of existence, like what does it mean for something to exist?
Mm-hmm.
I don't know what it means to say that something can exist outside of time.
Yes, great question. And in a sense, at the level of possibility, we really do, it's not like you lose time, but there's a form of time that is more of an internal kind of time. It's not the temporal, the metric time interval by which you measure, events in space-time. in fact, there's a physical counterpart to it. So the physical counterpart would be, we're composed of matter systems that have an amount of rest mass. And this is in contrast to photons, which are massless. They have no rest mass. There's no frame in which they are at rest. So, but for ordinary matter, which has this rest mass, those types of matter have a kind of an internal periodicity. So, and in a technical sense, you can relate it to the spin, to these spin 1/2, what are called fermions, objects such as electrons and protons and neutrons and so on. And they can almost be thought of as kind of forms of trapped light that are not really explicitly space-time objects, but they kind of carry with them what we would call an inertial frame. And an inertial frame, that's kind of a coordinate system, if you will, that you can sort of use as a map to describe events that you experience, but it's not really part of, it's not like a space-time container. It's really an internal clock, if you will. So it's I'm not sure that helps at all, but it's not, we're not doing away with time. But it's a kind of a time that's really more of an internal reference for these matter systems. So they can be thought of as evolving, but at the level of possibility. And their interactions give rise to space-time events. So these events are kind of then the events which are parts of the transactional process, the emission event, the absorption event. Those are simply, those are elements of space-time, but there's not really a whole lot to space-time. It's basically just a set of actualized events that have a certain kind of relationship among one another. So I'm not sure that helps, but
yeah, I'm not sure. I'm trying to kind of process what you're saying. I think maybe I'm a little bit ignorant of some of the terminology. I don't know. How would you? I mean, maybe let's go to as basic as we can. Like, how do you define a field for those that are watching who are not, who don't know anything about science?
Mm-hmm. Well, a field, it depends kind of which level we're talking about. A quantum field is actually a mathematical construct that is very abstract, and it really just refers to the possibility of say, if you're referring to like the electromagnetic field, the quantum form of the electromagnetic field, the orthodox way of representing that would say that it's a bunch of operators associated with every space-time point. Well, I don't think space-time is a container, that is characterized by a bunch of points that may or may not be occupied. But that's kind of a standard way of thinking of it. That's the orthodox picture. Now, what is an operator? Okay, it's can create or destroy a so-called quantum of the field. So this is all very abstract, and it's a picture that I'm just trying to. The term field is just a very fraught term, but it's kind of on one level, it's a mathematical construct that can represent certain kinds of physical interactions and so forth. The better way that I think we can deal with the concept of the field is by thinking of it as a relational entity. So that, for instance, in this absorber theory, in the direct action picture, the electromagnetic field is really kind of a connection between these charged particles, so that you can have these different charged particles, and you can quantify their relationship in terms of an interaction. How likely is it, say, that some atom will emit a photon to some other atom, and so on. So in quantifying those things, we are dealing with the relationship between those sources. We can call that a field, and it has a different kind of mathematical representation, usually using space-time parameters, but not always, sometimes using momentum and energy to characterize it. But as you can see, I mean, it really depends on the context, and there's disagreement about, well, what counts as a field? You know, do we really have this notion, this thing that we call the quantum electromagnetic field? Is that really a freestanding system? And again, I think it isn't. So it depends on what kind of theory you're using. But in general, I guess one could say, well, a field is a kind of a spread out object as opposed to a localized object.
I see.
So they're an extended kind of object. So there are different ways of characterizing and quantifying how, in what way is this an extended kind of entity.
So I have some questions from the audience, but before I get to those, I want to try to ask one other thing from my standpoint. Because you were talking about this idea of almost reality on some level operating outside of what we call this kind of timeline, right? So is the idea that the timeline is more of like an emergent feature that's kind of not looking at the whole picture, and so it's almost like if we step back far back enough, then we see that, I forget the exact term you use. Was it almost like a present, like an eternal
like an
present?
Eternal present, yes. Yes.
And so why does a sense of passage of time arise from this eternal present? And in what sense does it make to talk about causes and effects and relationships among phenomena, if we are removing those things from a notion of past towards future?
Okay, so I guess I should clarify that, strictly speaking, the transaction, the time symmetric form of the field only applies to photons. So that only applies to the massless photon, in which we have this kind of a time symmetric sort of no arrow of time applying at the level of that's at the level of what's called virtual photons. So it's at a very basic level. It's a form of a relation among these charges, which do have rest mass, and they do actually have an intrinsic arrow of time. They do have a clock, so they have a kind of a sense of flow on their own level. They do have a sense of flow on their own level. So objects with rest mass, non-vanishing rest mass, do kind of carry with them a form of temporal flow by virtue of their internal clock. But photons don't have an internal clock. And the way you create a photon is through this sort of time symmetric field. So the time symmetry really applies to the creation of what we call space-time events. So at the level that's beneath that, at the level of possibility, the rest mass systems actually do kind of bring with them this intrinsic arrow of time. So they do carry that, but it's not that, but they're not, that's a separate issue from events. Events are actualizations, and these are possibilities. So you can think of it as like possible time. So it's kind of a template for, time for causality, but there's nothing actualized yet at that level. The actualizations involve these transactions, which then give rise to events. And it's actually the set of events. The only thing that is, the irony here is what we call space-time has in it neither space nor time in any fundamental sense. All it is, and this is, Einstein actually said this, he said, the space-time manifold is simply a collection of events. And their connections, okay? And you can, and the whole point is, you can pick different reference frames and have radically different ideas about how much time has passed between two events and so on. So time is really, it's not, neither space nor time are really, they're concepts that we use to coordinate our experiences of events, and to be able to communicate and corroborate that event and say, yes, we all agree this event happened, and we can corroborate it because itself it's invariant, and its connection between the other events, those are invariants. But our descriptions are radically different, and those descriptions are based on this internal kind of reference that we bring with us as at the level of possibility.
Let me read you some of the comments.
Okay.
What does Dr. Kastner think about the very recent EPR, ER ideas?
Let's see. I think that's the idea that the EPR correlations are carried out by way of these Einstein-Rosen bridges, which are supposed to be like wormholes and so on. And I don't think we need that, because, I mean, I think that the idea of a wormhole is invoked to try to explain the non-local, interaction. But that's from the usual viewpoint that that everything is in a space-time container, that everything real is in space-time. And so, and what I do, I question that. I say, no, I don't, real things are not, space-time is simply this emergent kind of tip of the iceberg, actualized events, structured actualized events. And a lot of what goes on physically is happening at this level, pre-space-time quantum substratum. And so if you allow for that, then these non-local, the EPR, the Einstein-Podolsky-Rosen correlations, are simply natural, instantaneous relations, communications among possibilities, because that's the way possibilities are. They have this relational quality, and they're always in contact, in a sense. In a broad sense, they're sort of all in the same place at the same time. So there's no remote kind of, you don't need to worry about sending a light signal, because that's not what you're doing. So that's what I would say. I don't think we need the Einstein-Rosen bridge.
Next one. Is Heisenberg's probability problem due to the inability to measure without changing the measurement?
So, well, the Heisenberg uncertainty principle does reflect that. Yes, the idea that that possibilities, that quantum systems are, because they are possibilities, they have propensities to have different kinds of outcomes and so on. And really, at a fundamental level, the more basic properties are things like momentum and energy. So when you want to measure what you're calling position, you are definitely going to be interfering with the system's momentum, because you're going to be interacting with it and catching it and either speeding it up or slowing it down and so on. So there is interference in that way, but it's a broader issue. It's not so much that simply that we're disturbing something, but these kinds of objects do not really have determinate properties for different kinds of observables. What we're calling an observable is a mode of interaction with the system that will generally tend to localize it. And because quantum systems are not naturally localized, when we want to go, we want to answer a question like, where is this thing? Well, it's actually all, it's in a lot of different, it doesn't have to commit to being localized, because in the quantum substratum, things aren't localized in that sense, because they're not events, they're not actualized. So these potentialities are kind of much more expansive than can be manifest. That we can't. It's sort of like trying to look at both sides of a coin at the same time. Clearly a coin has two sides, but if you want to toss it, it's always going to land one way or the other, and that's kind of what we're doing with these measurements.
Right. I guess one question that always arises is like, in what sense does it, what does it mean to say that these things are real, that these possibilities are real, if it seems to me like what is real is the actual event that's actualized.
Right. So that's a great question. I mean, it challenges our assumption, our ideas of, well, what does it mean to be real? And that's a very big issue. and what I like to kind of remember, well, Ludwig Boltzmann, way back, when I'm not good with dates, but when he was developing the kinetic theory of gases, he proposed that, maybe we've got these little things called atoms that are unobservable. Okay, they're in principle unobservable, and so empirically they were suspect. This goes back to the idea that, to be a respectable concept in physics, we want things to be empirical. And that's a noble, that's a laudable approach. We don't want to go off in flights of fancy, but you can go too far with that. So the tradition back when Boltzmann was proposing atoms was very much, if you can't tell me how to detect this atom, then you shouldn't be talking about it, and it's not a real thing. But in fact, the theory that he came up with based on proposing that atoms were real it was incredibly fruitful, and we wouldn't have modern physics without it. So the idea is that sometimes it's worth allowing that an entity could be physically real if you can show, based on a theory or a model, that it predicts empirically corroboratable results, and so it's fruitful in that sense. It's yielding fruit, and it's kind of, you could say, well, I don't consider that real, but then you have the problem where, well, if it's not physically real, then why is it giving rise to concrete experiences and phenomena that we can corroborate? So then you have to say, okay, well, how come just some dumb idea in your head is doing things in the world?
And
right?
they actually have an empirical basis.
That's right. So indirectly, we're seeing that, saying that these things are real and saying, here's how they behave. Here's my theory. It's getting dark here, so I can my light's going down. But here's my theory of how these things behave. Well, they're kind of strange because their mathematical character doesn't seem to fit into space-time, because the other issue is that these quantum states are complex. They have a complex mathematical character. Means they have an so-called imaginary component to the state that describes them, and they're many-dimensional. If you have more than one quantum system in one of these correlated states, then you have far more dimensions than three. So if these quantum states are describing something real, well, they must be kind of something strange, that doesn't fit into space-time. But nevertheless, it doesn't mean they're not real. So that's kind of the approach I take.
Is it becoming more acceptable to philosophize about quantum theory in recent times? Are we beyond the shut up and calculate approach?
I would hope so. I think kind of depends who you ask. There still is a lot of, I think, once again, the physics community, I feel is somewhat reluctant in general. Not everyone by no means, but in general, there is a sense of fatigue with trying to understand quantum theory and so on. Very much though with philosophers, philosophy of physics is still trying to understand it and get an idea of, well, what are the implications for our understanding of reality.
Okay, here's the next one. That we should consider as real fields that travel backwards in time seems more like the purview of a magician than a scientist. In what sense is backwards causation in physics compelling?
So yeah, there are a lot of terms here that maybe I need to disambiguate. So these time symmetric fields that seem kind of bothersome when we're all kind of used to, thinking having a certain concept of the way things work. They aren't. Again, these are influences that are not in space-time, so they're not literally traveling backwards in time. They're kind of the time symmetric. Our language is kind of limited. Here's where we arrive at a limitation of language. It has a particular mathematical quality that the best thing we can come up with for this, the object is called the time symmetric propagator. And if you kind of look at it in mathematical terms, it doesn't say, hi, I'm going back in time and I'm going forward in time. It doesn't really have that, that's kind of verbiage that is a way to kind of gesture at well, what are these fields doing? But it's not really all that accurate, and it's not the usual. I mean, I know a lot of people think of the transactional picture that way, where that supposedly the future is sending signals back to the past, and no, that's not happening at all. And in my development of the interpretation, I've tried to be a lot more careful about that. So we have so-called advanced solutions, but they really describe the relationship of the energy, energetic quality of the field with the objects that it's interacting with. And really the basic point is that when you've got this connection, what they call a time symmetric field between two charges, all it really means is there's no fact of the matter about which charge generated it and which charge received it. It's mutual. So that's really the quote time symmetry. That's really all it means physically in this formulation that as I've developed it. I mean, I think the original, Kramer version had the language about the stories about things going backward in time. No, that's not what's going on at all. So it's at the level of the quantum substratum, and in a very real sense, these are virtual photons. Only virtual photons are the ones that have this purely time symmetric character. And again, all it means is there's no fact of the matter about which one's generating which one. It's mutual. And that we even have that with standard quantum field theory with the Feynman propagator, where we have you don't want to say for virtual photons, you're not allowed to say which direction it's going. So we even have that in standard quantum theory, and it's really something that applies at the virtual level. So I would urge this reader who's clearly got some background and some concerns. I do have my my book that was the first edition came out in 2012 on this formulation, and I just now have the second edition that came out from Cambridge University Press, and that's available widely now. So it's called The Transactional Interpretation of Quantum Theory, a Relativistic Treatment. And I think if you look at that, you'll see all these details spelled out. So we're not having reverse causation or anything like that.
Gotcha.
Yeah.
Next one. So the space-time of general relativity emerges from the transactions in the TI approach?
Exactly. That's what I'm proposing. And I am working on what would be essentially a form of quantum gravity that spells this out in quantitative terms. And of course, it's a different understanding of the idea of quantum gravity, because in this picture, gravity is not a quantum field. It's simply a process by which these events emerge from the quantum level, and then have that the structure of the events is what's described by general relativity. So that's exactly right. Yes.
Someone commented, I don't think the doctor could falsify unactualized events in her hypothesis. How would you respond to that?
Yeah, this isn't something that, you can't say, hey, here's how we would detect an unactualized event, so clearly there are things you can't detect. But again, this is where I go back to the idea of you can judge a model by how well it can explain anomalies. And so what we get from the transactional formulation is a lot of the anomalies of current physics get resolved. Anomalies such as the measurement problem. We have a bunch of other anomalies. We have, again, things like dark matter and dark energy, which are also resolved in this approach in which you get space-time as an emergent construct from this actualization. You don't need to postulate dark matter and so on. So those anomalies are resolved. And we have other anomalies such as there's supposedly infinite vacuum energy in standard quantum field theory. That's problematic and kind of embarrassing. And we get rid of that also in this approach, because we don't really have this existing field structure that's sitting there that gives you infinite vacuum energies. So this so-called zero-point energies, that's actually doesn't happen in this picture. So there are a lot of anomalies that get resolved.
Is this comment accurate? They're saying you're referring
Not
to a term.
quite. So again, I oppose the idea of a block universe. So what in the picture that I'm offering, the space-time manifold is actually growing. So it's growing, and not in the sense that you would see on Wikipedia for growing universe, but it's not a static block world. In fact, the notion of an eternal realm does not apply to the space-time construct, but rather to the dynamic quantum substratum that doesn't really have a space-time actualized temporal, doesn't have temporal relationships with other events because they haven't been established yet. So that's kind of the way I'm using the word eternal. So yeah, I'm not the whole Minkowski direction was kind of a way to be able to draw space-time diagrams and get a little bit carried away with the idea that when you draw a little map and put events on a map, that somehow that describes reality, but you don't need to go there really. Yeah.
Right. Well, this isn't really. Let me see. If you guys have any other questions, just leave them in the comments here.
So I do have, depending on what level you're, I hate to do a shameless plug, but here's my second edition. So that's the second edition that does lay. I don't know if you could see that or not. So sorry, the light is not very good here.
So the title is Transactional Interpretation of Quantum Mechanics, a Relativistic Treatment.
Right.
So if any of you are listening or interested,
yeah. And that's the second edition. And then I have a couple that I wrote more for the lay person that are less technical, that lay out the concepts. So if you're kind of puzzled about the concepts, this one is, I always have trouble with my understanding our unseen reality. Okay, and this is from World Scientific.
Solving quantum
riddles. And then there's a follow-up to that that's called Adventures in Quantum Land.
Exploring our unseen reality.
All right. So, and I do have a little animation that I designed that it's very quick, little 1 minute. I think it's only about 1 minute animation that I can give you. Maybe later I can write in the comments under the YouTube. Yeah.
That'd be great.
So that's something people can go to that just gives a little quick illustration of the idea of a lot going on in what I call quantum land. It's kind of a fun term, for basically the quantum substratum that I think quantum theory is pointing us to and saying, yeah, this is part of reality. Okay, it seems crazy, but it does seem to be fruitful in various ways. So it illustrates the idea that you've got these interactions at this quantum level that can, under quantifiable circumstances, it's probabilistic. But it's quantifiable. And that you can get these transactions in which you kind of extract like a thread of space-time, an emission event, an absorption event, and that comes out of this level. So that I'll put that in there later.
Thank you so much. I appreciate it.
Sure.
And also, if you want to, in other comments, put the names of the books so people.
Sure. Okay. Yeah, I'll put that in. Yeah, make a note here.
Begin to Know asks, did you set things straight with Tim Malton?
So yeah, I don't know. I mean, okay, so Tim Maudlin had this objection to Kramer's version of the transactional interpretation a while ago, and it basically doesn't. There was kind of a thought experiment that he came up with, and he said, "Oh, I think this is problematic for various reasons." And it was a nice, it's a good example of what philosophers do, raise challenges for one another. And I like that. And I think it was a good way to kind of say, hey, you maybe need to make this more precise or whatever. And what I found was when I was developing the relativistic form of it, that you actually you never get the situation, the physical conditions that arise in that thought experiment. So it was a kind of an understandable concern if you're using the usual kind of paradigm where we live in space-time and, causation has to go this way and so on. And, how are things going to go backwards and forwards in time? And Are we going to run into causal loop problems and that kind of thing? But you just don't get that at all when you have this picture of for one thing, the relativistic level, where you just could never have that kind of situation where we had a slow-moving offer wave. You would never get that kind of entity. And I explain that in detail in my second edition and in preprints that are available also. But so yeah, so I mean, and I don't know, I haven't personally heard from Tim as to his opinion of it, but you know, I've shown that's no longer a problem.
Gotcha.
Yeah.
Yeah. If any of you have any other questions, we're closing in on the hour here, but while I wait for that, I just want to thank you again for being here.
Oh, well, you're very welcome. Thank you for inviting me. It's always a pleasure.
I want to say, and this may rise from my ignorance in the field, because I very readily admit that a lot of this, I think, goes over my head. I'm trying to understand conceptually what is meant by a lot of these concepts. On an intuitive level, I really struggle with understanding the meaning of, when you're talking about potentials and you're talking about this idea of an eternal or of an unactualized reality. These are things that intuitively, I think I run into like a linguistic wall where I'm not, and I hope you don't take this, as in the wrong way. I don't mean it to be in the wrong way. It's just, I'm not sure. I don't know what is meant. It's almost like when I hear it, in a way, it reminds me of when I hear theists talking about how their interpretation of God is of an entity that exists outside of time. And while I understand that the difference here is that even if kind of the background seems uncertain or really abstract, well, at least the science has this body of an empirical basis, that at least there's still something there that we can point to and say that we're still doing science, even if some of our concepts seem really abstract and counterintuitive. I think I run into that wall on an intuitive level where I'm not sure what is being said by the sciences. Like how are we even talking about reality if we're talking about these potentials that aren't actually, I guess that's what I mean.
Yeah.
Like reality.
So maybe if we make it more specific and just say the term actual has a very technical, narrow meaning in my proposal. And what it means is space-time event.
Yeah.
So, but again, space-time is just a phenomenal, superficial level, so that reality is deeper than that.
Right.
And so our theories are the beauty of quantum theory. And I mean, if you look at the history of quantum theory, it was sort of nobody wanted it, nobody ordered it. They were like, oh my goodness, this is terrible, I don't want this. Right. So Heisenberg was really struggling, and he kept trying to make models that look like space-time things, that look like concrete, things that correspond to space-time events. And it utterly failed. And he just said, okay, fine, I'm just going to make a list, this abstract list of different, the energy levels of an atom. Okay, they're discrete energy levels. And I see the probability of seeing that one after I get that one was this. And he made what it's called a matrix, and he didn't know that at the time. But he called it a laundry list. So he did kind of this Zen beginner's mind thing. And he said, okay, nature, I don't know, my models about what I think reality should look like, they're all failing. So fine, you just tell me, what is the mathematical relationship here? And he wrote that down, and he had this mathematical construct that worked great, and it started working great. Well, then Schrodinger came along, and he wanted to make it correspond more like something he could intuitively get his hands on and say, well, maybe it's a wave in space. I want it to be a wave in space, so that he came up with his wave equation. But it's not a wave in space because it's complex. So it's this whole tradition of people trying to get this mathematical apparatus that worked great. Nobody wanted it, but it was necessary in order to make progress in predicting, empirically corroborating, predicted phenomena. So they had this terrible mathematical monstrosity, and I'm sorry to say, folks, that's what describing reality, and whether we like it or not, the theory, we can be anti-realist if we want, and a lot of people do that, and they say, okay, well, it's just a tool for predicting phenomena, and a good scientist doesn't say that it's real. But then we run into Bohr's problem, because Bohr would say things like that. He would say things like, this is a very loose quote, we're paraphrasing, where I, sorry, Bohr, if you're around. But he would say things like, quantum systems, there is no quantum world. You go an anti-realist. Quantum systems are abstractions. Their properties becoming well-defined only upon interacting with the measurement apparatus. Well, I mean, I'm sorry, but that makes no sense. If you want to deny that a quantum system is real, then how are you you're claiming that it interacts with the measurement apparatus? Well, presumably you think your measurement apparatus is real, but now you're saying the quantum system is not real. So what's this interaction? So you see, when people try to say, oh my goodness, this is too crazy, these things can't be real. I'm a good scientist. I'm a good physicist. I don't fantasize about angels dancing on the head of a pin and this garbage, right? When you try to do that, you end up saying just crazy, self-refuting things. Right. So it's sort of, it's something we need to try to understand. But again, the notion of space-time, it's a bad word, because really it's just certain actualized events, and we can describe them in different ways. And the terms space and time are just ways that we have for describing them.
Is it fair to say that we have a quantum formalism, but no consensus on a quantum theory? Are we making progress on the consensus issue?
It's an interesting, that might be a nice way of putting it. I actually think the current formalism, however, is flawed in that, again, it's using this kind of unilateral notion of field propagation. So, what I'm doing is, what I'm offering is a slightly different formulation of the theory that has a different way that the fields behave. And again, it's a little bit troublesome for those of us who are marinated in the standard way of thinking. But again, it resolves these anomalies. And as far as consensus, no, I'm sorry, there's no consensus. And I think that's a reflection of how troublesome the standard approach still is, and the transactional formulation is still kind of a little viewed dubiously. So I think once people start, reading it more, realizing that it does in fact resolve these anomalies, that we might start to get more consensus around that.
Okay, I will read one last question here.
Okay.
Would Ruth mind commenting on the speculation among physicists of offering an explanation of dark matter as an emanation of a universe with a backwards flowing time?
I think I heard something about that, and I don't really know enough about it to comment. But I feel like that comes from an idea that space-time. Space-time is kind of the container that we all live in, and it's space-time itself that has this flow, and that will kind of do the mirror, universe, and see if that gives us something about dark matter. So I think, I can understand why people might want to explore that, but I do think that we really get what we need from the understanding space-time as emergent in this way, because then we find that you naturally get the kind of effect or the change, the generalization of general relativity that allows you to see why you're going to get this behavior that we attribute to dark matter.
Should scientists be able to reduce their conceptual systems and the individual concepts which make them up back to perception in the positivistic sense?
Well, I don't think so, because I think that, once again, perception is kind of the way we corroborate the predictions of theories. But it's again, I think that's what tripped Bohr up, because he didn't want to allow quantum systems to be real, because you couldn't observe them. And I think if we make that a criterion, and we really foreclose a lot of progress. And again, if people had done, in fact, they did that. They tried to do that with Boltzmann, and Ernst Mach was very much kind of an antagonist to what Boltzmann was trying to do. And he made that claim. He said, look, you can't tell me how I could verify the existence of your atoms. So, please stop doing this. It's irresponsible. And in fact, he was wrong. So I think that when we're being creative, when we're coming at, theories about what's a good way to unify the way we're approaching things. And in fact, that's what Einstein did. He didn't use perception. He had some thought experiments, but he came up with his postulates that led to special relativity through theoretical consistency criteria and so on. So he wasn't saying, I need to be able to see this, or I'm not going to develop my theory. So I don't think we want to limit ourselves in that way.
And finally, great guest. Please have her back.
Oh.
Thank you, Dr. Kastner.
Well, thank you very much. It's been a pleasure, and I really enjoyed all your questions. So yes. Thank you.
Thank you again for coming on, and yeah, I would love to have you back.
Okay.
Sometime in the future.
Well, thank you very much.
So, and guys, as always, thanks for having joined us tonight. If you want to support what we're doing, patreon.com/Axioms on Trial, or like and subscribe to the channel and the videos. And we'll be back again soon, in a few days, with another episode. So I hope that you guys all have a safe night, and I will see you next time. Thank you.
Good night, everybody.